So let's start this session. So here we're going to discuss about the independence, basis, and the dimensions. So what is all these? We'll see one by one. So the true size of the matrix is not defined by actually the R, or if we see here. So if there are n columns in a m by n matrix, but the true dimension of the column space is not necessarily m. The dimension is measured by counting the independent columns. So now we have to define what is meaning by these independent columns. It means the true dimension of the column space is the rank row. So let me write these points here. So if you write the point here that the true dimension of the column space is the rank R. The true dimension of the column space is the rank R. So now we will see, we will understand what is the meaning of this free or the independent columns, which defines the actual size of this column vector, the dimension of this column vector. So now if we consider that the whole idea is that the idea of the independence applies to the vector v1 to vn in the vector space. So then we will concentrate on the subspace here, and the important goal here is to understand the basis, that is the independence vector that spans the space. It means the independence vector is one by using which we can fill the entire space, the column space. We can fill the entire column space, or if we write the definition here, then every vector in the space is a unique combination of the basic vectors. So that is what it means. So let me write the definition also here. So every vector in the space is a unique combination of the basis vectors. So all these vectors, every vector in the space is a unique combination of the basis vector. So here we will discuss few essential concepts, ideas. So that also I'll write here. That is the independent vector. We'll talk about the independent vectors. So it means no extra vectors. Second, we'll talk about spanning of space. So it means it has enough vectors to produce the rest. Then we'll talk about the basis for a space, not too many or too few. Then fourth is dimension of a space, then the number of vectors in a basis. So this is the meaning of all this. Now let us see the definition of the linear independence. What is the meaning of linear independence? So the definition goes like this. The columns of A are linearly independent when the only solution to Ax equal to 0 is x equal to 0. No other combinations Ax of columns gives the 0 vectors. It means if you look into the previous example there, so we had found in the null space that Ax is equal to 0, so that will give the the special case solutions if you have the free columns. And if we take out the free columns there, and if there are no free columns, then what is the actual value of x? So then the value of x has to be 0 to match it with the right hand side, so that is equal to 0. It means for the 0 vector. So that is what this linear independence definition says. So So let me write the definition here. So it means that the columns of A are linearly independent when the only solution to Ax equal to 0 is when we make x equal to 0. So then there is no other combination Ax of the columns gives the 0 vector. So this is one form. There are such kind of many forms also exist. If the value of x is not equal to 0, it means in that case it becomes a dependent case. So that's a dependent case. So now just to understand this, so let us take an example. If you have 3 vectors, and if all these vectors are not in the same plane, if it is in a different plane, so if I draw here the 3 vectors, for example, it is like this, and one vector here and the other vector here. So all 3 are in the different space. It is not in the same space. So this is v1, v2, v3. So these are the 3 different spaces. If the vectors are in the 3 different spaces, then you cannot combine them to get the 0. That is, we cannot get this except only one condition. That is, we have to make this 0 into v1 plus 0 into v2 plus 0 into v3 to make it, bring it to 0, means to make it equal to the right hand side. So right hand side is equal to 0. So how do we combine all these vectors to bring to make it equal to the right hand side, that is to the 0? Only by making it all the multipliers or the scalar values of these vectors equal to 0. So if you do this, then only we can make this is equal to 0. Or the other example is, for example, we have a reference point here. If all these points are in the same plane, so if you see this, all these are in the same plane. If I call this as w1, w2, w3, so now all these 3 vectors, that is w1, w2, w3, are in the same plane, but now they can be combined to make it equal to the right hand side, that is equal to 0, but these are not the independent, so now these are called as the dependent vectors. So likewise, if we look into the if there are the 7 vectors in a 12-dimensional space, so then they are the columns of A, and the independent and the null space for the x equal to 0. None of the vector is a combination of other 6 vectors, so that will result in that kind of form. So let us write the one more definition for the linear independence case here. So if I write the definition here, it means the sequence of vectors, that is v1, v2, dash 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 up to say vn, is linearly independent if the only combination that gives 0 is, what is the only combination? So now if v1, v2, v3 are in a different plane, so what is the combination? It cannot be combined. So to make it equal to the right hand side, that is a 0, so only thing is that we have to multiply all these vectors by 0. So it is 0 into v1 plus 0 into v2 plus etc. like that. So 0, so it is plus 0 into vn. So that is the definition of this. So now the sequence of the vector can be either dependent or independent. So we will see the special case for a 2-dimensional case. We will see the special not special solutions. We will see some particular kind of vectors which can be independent and dependent, and that will give you the solution which is equal to the right hand side, that is 0. Means it will give us the 0 vectors. So for that, let me go for the next page. Let me save this page here. So page 104. So now we have considered that the two-dimension space, so therefore it is we can write this as R square, and the combination of vectors. What can be the combination of vectors in a two-dimension space? So the vectors can be either 1 comma 0, so this is a one vector, and one more vector is 0 comma 1, or independent, and this will give the 0 vector. So if you see this, if you uh, so these are independent, so these are in the same plane, and also it is independent vectors. So the second one is the vectors, that is 1 comma 0 and 1 comma 0.0001 are also independent, and the third kind of vector is that the vector that is 1 and 1 and -1 and -1, so these are dependent because it lies on the same line. 1 and -1 will give on the first quadrant, -1 -1 will come in the third quadrant. It means it forms a line and pass through the origin. So therefore, so these are dependent vectors. So fourth, and the vectors 1 comma 1 and 0 comma 0 are dependent because of 0 vector, because it starts from the 0 vector. And the fifth point is in R square, just read it as R square, any three vectors, that is AB and CD and EF, are dependent. So these are the vectors which results in dependent and independent vectors, which will give us, it can be dependent or independent vectors, so which will give us the 0 vector in a two-dimensional plane. So if you continue with the same example, if you look into this third point here, so then if we take those vectors here, so if I take this vector that is 1 1 and -1, so if I take this vector here, so this is nothing but this is equal to the two variables here, that is x1 and x2, so which should be equal to 0 and 0. So if I want to make this equal to 0 and 0, what should be the value of x1 and x2? The value of x1 and x2 should be 1, and the x2 value should also be equal to 1. So that will give us the 0 vector space. So the columns are, we call it as a dependent when there are non-zero vectors in the null space. So when there are non-zero columns, non-zero vectors in the null space, so those kind of vectors we call it as a dependent case. So let's take one more example here. So for example, we have taken here that is AX is equal to, we have the matrix that is 1 0 3 2 1 5 2 1 5 and 1 0 3, then we have -3 1 1. So the actual let's try to solve this. So if we solve and bring it to the reduced form, so how do we get it? So these are the x values, so let us forget about this for time being, so this we can find it later. So let's solve the matrix A. So if we solve the matrix A, so we'll go with the same reduction method here. So first row will remain to be as it is, then the second row will multiply the first row by 2 and subtract by row 2. So here I'll get here 0, so here I'll get as 1, and this I'll get here as 3 is 6, so I'll get -1, and this is 0 0 and 0. So third row has completely become 0. And now if you see this, so what happened here is that the third row is completely 0. So it means rank of the matrix here it is equal to 2 because there are only two pivots. So one pivot is here and another pivot is here. And how many so if we talk about the null space solution here, so null space solution Ax is equal to 0. So we'll make the 0 and we'll send this. Now this has become the free variable. Now which is the free variable here? So this column, the third column, has become the free variable. So now then I can write this as, say, x1 is equal to 1 0 plus, I can write this as x2 is equal to 0 1, which is equal to minus of 3 and 1. It goes on right side, so minus of this, so minus 1 plus. So what is the value of x1 and x2 that I'll get here is that, so x1 value is, I'll need to be 3 here, so and here this value has to be minus 1. So it means if we look into this case, so it is minus 3 and minus 1. So minus 3 and plus 1. So now this we got, that is the values of this. And what about the x3? x3 has to be 1, then only we can take it to the right hand side. So this is a dependent case here, so this will kill the independency. So if we look into this example here, so x is equal to, we have a solution minus 3, 1 and 1. It means this is x1 is equal to this and x2 should be equal to this, and here x3 should be equal to 1. This is my x3. So then what is the special solution here? The special solution is nothing but here, that is a minus 3, 1 and 1. So that is what we have written here. So it shows how the free columns x3 is a combination of the column pivots. So it means if you see here, the free column is a combination of the pivot columns, but it will kill the independency. So that is what it means. So now let us look into the one more final definition of this, then we'll wind up this session. So the full column rank of A is independent exactly when the rank R is equal to n. So let me write the definition here of the full column rank. So full column rank is the columns of A are independent exactly when the rank is R is equal to n. When the rank R is equal to n, when the rank R is equal to n here, then there are n pivot and no free variables. So the condition is that there should not be any free variables and there should be n pivots. So then only that the column independence will comes into effect. So in this example which you have seen, there is one free variable which we have considered, that is x3. So we have not neglected it. We have considered that free variable and then we have tried to find the solution. And here the definition continues that only x is equal to 0 is in the null space. So that's it, and we will continue this in the next session, this independence case and basis. We'll talk about more on this in the next session.